All right, so 2 years ago, or probably last year, when I ran this project, I didn't give them any materials. It was just a official ADC tutorial from Digilent, I think. And so they reached to a point that they can acquire data from the XADC from a potentiometer, and there were 3 groups. I think Taylor and who else was on one team. They figured out a way to skip 8 data points and eventually log the last one, the 9th one. And Ian and Mason were trying to, so they saw the same issue, but eventually they gave up on the traditional method. So what they did is they used the Arduino to write their own SPI logic instead of using the SPI.h header file. So they look at the timing and write the timing in C by themselves. And it seems like that worked as well. So remember last time we were talking about why we have to skip 8 data points? And I was thinking about having a data latch in the middle. Right here's the ADC. Analog input, we got data here. So name of the output is actually data, right? So it's a wire input in the top. And you have your SPI. So SPI also has a data, it's an 8-bit bus. So in the middle, if you have a latch, I call it data latch. And you use this, because the SPI forward transmitter has a busy line. So whenever it's ready for the byte, so whenever all the 8 bits in the byte getting transmitted through that missile line, 1 bit output, right? And this one gives a 0, right? If this is 0, it latches the data from here to here, okay? Looking at this signal line. So remember we talked about this during the lab last week. It didn't work. I implemented it last night. I was trying to, probably I want to do it for them because there are so many other assignments for the remaining 2 weeks. So I'm going to do this first. It didn't work, so that's the bad news. The good news is I tried, I came back to Taylor's method and dropped 8 data points and only take the nice one and it worked. We'll pass this task on to the next year's students, right? So now I give example will make your life easier. Given that I have to travel this week, I hate it a lot, but I just have to. So you'll get less help from me. So I did it for you, it worked. So what you can do is just see if your hands are good enough to duplicate my stuff on your end. So you are done with the digital part of it, okay? So the digital part is done, then you can solder your PCB. Hopefully it's gonna arrive today. So I'll give the PCB before I leave. So my flight is at 3 p.m. I think. So if the receiving department get it before 12, I will be able to put it into the 602 lab. You have access. I'll let you know where they are, so you can grab the parts. And the DigiKey surface mount parts are right here. You got a PCB, you got surface mount parts. You can start the soldering either before Friday or after Friday. I'll be here Friday afternoon. It seems to be a little bit late, but let's see if you have time today. If the parts are here today, you can start working on it maybe during the lab time today. Okay, the soldering should be pretty easy. As long as it works, it will be pretty easy. Okay, so let me show you some of the coding I did last night. It's recorded, so don't worry about that. The code is here. I don't have to use exactly the same code. So what I did compared to whatever Taylor posted over here. So these are pretty straightforward, okay? So what you have to do, she didn't show the constraint file, but what you have to do is export these lines in your top module But the thing is, there are not pin names of SS, SCK, and missile in your constraint file. So what you have to do is come to your constraint file, and I use the JB ports here. Can't zoom in here. Can I zoom in? Cannot zoom in. How can I zoom in? This guy? No, that's search. I have to use my mouse, but I have all the USB ports occupied, so I can not do it. Anyway, can you see it? Barely can see it. But I can tell that this is JB ports, right? So for JB ports, the JB1, I use JB1 as SCK, JB2 as SS, JB3 as missile. For other things, these SAGs, ANs are not really used, but you can use it because it's from the example. It's really nice. It's showing a decimal number on the 7-segment display. So it's really satisfying to watch, because when you are changing your power supply's voltage, you see a 0.6 volts, right? It's displaying us somewhere around 0.6. It's pretty accurate. You can use that one to verify your readout from that. And LEDs, it displays the binary number on the LEDs pretty accurately. And switches is used to. Oh, I didn't change the mode. We can try that later. But switches are used to define the mode of the SPI. And there's a clock which is 100 megahertz. Remember that this clock, the name is different from CLK. Okay. They use the CLK 100 amp hertz, it's megahertz. So in your top file, you have to use that same clock's name. Okay, so CLK 100 amp hertz. So LEDs has to be declared. Eventually, everything was sent to the LED for display. And you see here, that's the data latch I created. I can't zoom in, I'm sorry. How can I do it? This one. So register type, 8 bits, data latch. And what else I did? The SPI busy. Because the SPI has a busy line. Why that SPI's busy line is how that is being used? We can come back to the SPI's forward transmitter module. Once you need to know that, I'm going to upload all the code to my website. Okay, so you can directly use it. Because it's recorded, you can also watch the video and pause it and then type it. It just takes you more time. So I'll just upload it since it's already disclosed. And for the SPI module, you can see that there is a busy line here, right? This is module busy, right? So what's happening is whenever it pulls down the enable pin, it starts taking every single bit from the byte data input to missile. So missile is just one single output port. It's a serial line. So it's taking one by one using the index. So it's starting from MSB and decrementing that index by 1 each time. Alright? So whenever the index reaches 0, right? Reaches 0, it's done. And then moves to stop. So stop is gonna pull that busy line to 0. So which means after that entire byte getting transmitted through missile, the busy line will be put down to 0. So during the transmission, busy will be 1. Okay? So pulls it down to 0, which means the whole byte is done. That's why I was thinking that we can probably use that 0 signal, right, to trigger that latch and pass the data from the XADC to your SPI module over here. Right? That is why I'm using a See, this is a SPI SPI. This is the wire in the top module. So you can, after you instantiate your SPI block as well, you can connect that wire to SPI, to SPI SPI. To SPI SPI over here. See, SPI SPI and SPI BZ line. That's the wire in the top. So in that case, you can use this wire as a signal for the latch. Because this is the wire, right? Whenever you instantiate a module, this is the port available from the SPI module. Okay, you need a wire to report that line. So whenever this data becomes available at the port, there's a wire report. So this wire can report that that port of that sub module. So you use it in your if statement. So you can see the place that I used it was here. With SPI BZ 0, I'm sending the upper byte of the data because XADC has 16 bits, but we're only using the upper byte. So the upper byte will be sent to data latch. And data latch is the register type in the top, and data latch is shorted to where? Shorted to data of the SPI. Okay? So whenever BZ becomes 0, data, the upper byte of the data of the XADC is sent to data latch, which is a register type in the top, and that one is directly shorted to the data input of the SPI. That's how that works. That's how the code works. But eventually it didn't work. The code works, right? But didn't change the error messages we received, the 8 error messages. Didn't change anything, it's still the same, which is fine. I mean, we can still use this code. And I was trying to change you can see, I was looking at the oscilloscope. Okay, so probably the SDK and 100 microhertz are not getting synchronized for some reason, and but I couldn't see why. Eventually, possibly there will be some issues because of the unsynchronized signals. Then I was trying to use, probably just let's use a enable, because whenever SPI is getting enabled, the SS or CS is getting put down to 0, right? So I was thinking, can I use that signal line whenever it's getting put down? Whenever it's getting put down means SPI will get started. So I'm using that native edge to trigger that data latch transmission, the data exchange through the data latch. So I'm using like native edge of the SS, then I'm sending the data to data latch. I was trying to see if that helps. And also, I also changed this one to SS as well. So both are using the native edge of the SS to keep both sides on the same pace. That didn't help. Shows the same results. So I was thinking, hey, so the SPI on both sides are talking through the same signal. So I was using the 100 megahertz to update all the data lines. I was worrying about the speed mismatch. Because 100 megahertz as a clock for the XADC, it's just running inside XADC. It's working on doing conversions, and it's just making the data available at the output, right? It doesn't matter what else is interfacing with it because the clock is just being used for the XADC, all right? So it's just making the data available at the output. So I can use other signals to synchronize the communication of the SPI on the two sides. So I don't have to worry about the clock of the XADC. So I still keep the 100 megahertz clock for the XADC, but changing all the other two signals to update the SPI's signal lines. That's efforts I made, and it didn't help. Okay, I didn't even change the results. I didn't see any differences. So let's just come back to Taylor's methods. And so last week, Jake showed me one of the error messages, right? And there's a solution to that. You probably will see the same results because if you used whatever Taylor posted or whatever I'm going to post to my website, you'll see the same error message. So it has a concern about the clock wiring. you probably don't have to remember this, but I did some search on Google. Why Vivado doesn't like it? It's because you are trying to input a signal to the IPGA, because SCK is a signal line from an external device, which is Arduino, right? So you are trying to take that clock in and use it in your IPGA. So there will be whatever I saw was there might be an issue that the internal clock and that clock, they don't know each other. So eventually they are getting not unsynchronized on both sides. I don't know where that potential problem will be, but sounds like it doesn't like the design that when you input a clock to the GPIO pin for some reason. So there are some dedicated clock pins on the IPGA that I can use to input a clock into the IPGA, and I didn't find these pins. So Vivado, from the report, it gives you a solution to it, and I used it, that worked. So what you should do is put a single line of this into a constraint file, and then error message will be gone. Okay, so it's basically telling that disregard that clock pin, just treat it like a data pin or something. So it's gonna get rid of the issue. And come back to this one. If you add a data latch in the middle, it works the same way as whatever Taylor did last year. So it's basically no difference, or at least I was not able to see any differences just by probing it and eyeball it from Arduino's monitor. So the solution is still do a lot of data acquisitions and eventually only take the 9th one. So do 8 data acquisitions. This is a CS pin or SS pin. It getting put down to low or to 0, and then do the data transfer and put it up to high. So that's the SS. Okay, so do it 8 times, and then you got the 9th one, and transmit that one to serial. Okay, that's how we did it. It's not perfect, so again, we'll pass this on to next year's students. It worked, even though this, I don't have any power supply. I don't have power supply over here on the desk, but it's basically 0 volts. Okay, 0 volts, and it's not a. Oh, let me just connect to 0 volts instead of having any floating voltages or charges over there. So this one goes to 0. Input goes to 0 as well. Okay, it's more stable. Pretty much all zeros. I don't have a lower voltage because the lowest one I get is 0.0 volts, so I cannot connect to it. It's going to damage the IPGA. So I recorded the video, showed some pictures on it. Let me explain some of the. I'll pause it in the middle and explain to you what they are. Okay, so I switched to a different level shifter, and arguably this is a faster level shifter because I saw issues with the other one, but once I figure out the issues, I didn't switch it back. So I actually don't know if the one I gave to you would work or not, because I changed something on the circuit. And but anyway, so this one works. I'm gonna give you this new one, pretty soon, so you can use whatever the circuit I have on the breadboard instead of creating another one. I'm pretty sure have a lot of issues. So I talk about this a little bit in the video, and what's happening is there are 2 columns of pins, and on one side of these are 8 these are A pins called like A1, A2 until A8. And this is VA. So connect VA to 3.3 volts. And there's the OE. It's the enable pin. Enable pin should be put up to 3.3 volts. So I'm using a 10K resistor and directly just connect this pin to 3.3 volts through a 10K resistor. So here's the B pins. Here's the VB, short to 5 volts of the Arduino. And then it's the B1 to B8. And the last one is ground. So this ground is universal ground. You don't need another ground on the other side. So just ground this one to the universal ground of the entire system, and it should work. And that's it. So you can connect all the, there are basically only 3 pins, right? ICK, SS, and missile, right? So it's same on the other side. ICK, SS, and missile. I forgot the order, but the first one is ICK. I think the second one is missile, and the third one was SS. It doesn't really matter. You just have to connect B5 to A5 accordingly. If B5 is missile, A5 should be missile, right? Because it's like one channel from higher voltage to a lower voltage. And I used the JB pins.
It's a different level shifter, and so this level shifter is arguably a little bit faster than the one.
Picture of it.
I have 2 averaging the capability of able to display. The LEDs are able to display.
So JB pins, depending on how you want to modify your constraint file. So what I did over here is JB. I changed the JB0 to ICK, JB1 to SS, and JB2 to missile. So it's basically from the top three pins over here.
Display analog voltages.
Okay. Another thing is the XADC
look at the signal. Yeah, I have 2
I just did it, so I don't have snapshots. So I have to pause the video for multiple times. So you can see the 3.3 volts can be connected to this pin, and there's a ground. It's providing a universal ground to the ground rail on the breadboard, and all the other channels should be grounded. All right, and these are the inputs. So I grounded the minus input. It's a differential input, so I grounded the minus input. And I'm connecting this one, the plus input of the ADC, to the output of the potential meter. Okay, and this is the connection I have on the desk right now, and apparently it works. So it's not perfect because you can still see a little bit noises, some weird numbers inside, but these are pretty low numbers. I mean, there are cumulative charges everywhere. You'll never get just perfectly zeros, right? Even though I'm connecting everything to ground, it won't be perfect zeros. So another thing you can change is, these are just raw data, right? So if you are throwing this one to a display to plot, for example, if I want to plot a waveform of my fingertips signal, I can use a serial plotter, and it's just everywhere, right? And I believe it's because of the scaling issue. It's just the jumping from 0 to a pretty high number, and you might be able to get rid of the big numbers by it's a bit too high. You can use a low pass filter, or do a moving average, or whatever. So I'm not sure if this will show you a really nice waveform. I'm thinking that the issue is, since we don't know what's really happening, why it has to wait for 8 times, right? So let's do this and try it one more time and see if that will clean it up. I'm gonna skip one more data point. Yeah, I'll think about potential solutions in the airplane. So the plotter is not doing a good job. The serial monitor is doing okay job. You can see most of them are zeros. So how do we do the data processing? And I believe if you change the data to like maybe 100 or 50, it's gonna be like a bunch of 50s and have a little error message in the middle getting plugged into it. So definitely these data points can be filtered out by a low pass filter. But what else we can do, right?
Well, this is a few different things. You have something that removes like error and named messages automatically. Is there anything that's like not valid? Something remove that.
How to know it's not valid? Moving average, probably.
Yeah.
Yeah, let's see if you guys can find a way to do it. I'm pretty sure moving average is gonna work. Or maybe you just leave it as what it is. It's just, not perfect. All right. However, it's still a success because we are able to integrate the XADC with the SPI into a top module, and hopefully the PCB works so we can directly connect the output of the signal to our digital sensor and show the values over there. So it's still a pretty good progress instead of getting a perfect results, but it's getting one step closer to the truth. Okay, so do you know what the next step is for this one, for the digital sensor? Right, just copy the code. If you can improve it, improve it. If you cannot, just duplicate it and try to repeat the work. Still some progress. Okay, I did it for you last night. So again, these ones are unnecessary. It's not changing anything. If you just want to use whatever Taylor posted, I don't think it shows any differences. But if you don't see the results I'm getting here, you can always change it back to my code. Okay, like this. See anything else I need to talk about? Oh, there are a couple of typos in the SPI forward transmitter on the website. So I made the changes in this code. Like I said, I'm gonna post it so you can directly use this one instead of typing by looking at the code I posted to my website. Okay. If you want to come and take a look at the circuit on the breadboard, feel free to do so. And I'm gonna grab all these level shifters for you guys.